On est bon? Okay, all right. So let's start. Cool. So I do not have audio on this, and so to avoid copyright strikes, if you could just sing the first bar of like Heaps Don't Lie in your head, just to compensate for the fact that I could not include it in this presentation. Okay, you got it? Fine. All right. Oh, it's feedback. Bzzzt. That was scary. Okay, so you may have run into this guideline once in a while at a company, or maybe some guy on the internet or in some coding convention that just said like, don't use malloc. Just don't. It's bad. It's bad. You don't want to use it. Maybe you've seen something slightly more reasonable, like don't use malloc while the plane is in the air, or like once you started the gameplay, or in the rendering loop, or once you're start processing a request, something like that. Oh. Has anyone had like some kind of guideline given like that? Like you're not allowed to call malloc between this and that spot or whatever. Is that something somewhat familiar? Yeah, okay, some of you, all right. So I do talks about performance of late. I had made a bunch of talks. I wasn't sure what I was talking about as a theme, and I figured out like a couple talks ago that I was talking about performance actually. So I made a talk about profiling a couple 2 years ago. Then I made one about multi-threading. Then I said I would do this one, but I did them out of order. That's very computational of me. And then I did one on caches and data locality last year. So this is the one about allocations. And again, it's all about performance. So we're going to talk about especially memory allocation when related to performance. So I'm Mathieu. I'm a C++ programmer. I'm a game developer, and on the side, I'm a meetup organizer. I'm currently on a sabbatical. So I'm traveling. I'm just joining meetups and enjoying my time off for a while. If you happen to have a meetup, if you would be happy to have me, maybe I can turn that into a pretext to go traveling somewhere. If you happen to be in Stockholm, I help organize a game dev meetup, so if you want to show up or if you want to have a talk, feel free to ping me too. And if you have a very cool and interesting project, you can try your luck. I'm not going to say I'm going to be I might be picky, but you never know. All right, so what are we going to talk about? Yeah, we're going to talk about how does the heap work, like what is heap allocation, what does it actually do. I'm going to try to give 10 guidelines and a bonus one for handling memory allocation. And my goal is to have for beginners and experts alike. I've tried to ask people when I've done this talk in the past, like how many of those were interesting to you or new. I get some kind of a Gaussian, so I'm happy about it so far. And you can tell me at the end how many of the 10 were like interesting or new to you. So let's start with the basics. What's a malloc, right? Like, how many of you, well, first I'm going to define allocation, and then we're going to talk a bit more. So for the rest of this talk, allocation is the act of reserving uninitialized bytes on the heap, right? Or somewhere else. I'm not interested in construction. I'm not interested in zeroing. This is basically, you could say it's a C talk, but I don't do C. But, you know, conceptually it's a C talk, I guess. Likewise for the allocation, I'm only interested in giving back the bytes to the OS or whatever else. I'm not interested in doing any destructor side effect or whatever else you may have had. Cool. So let's start with just a frame of reference for stack allocation, which is maybe the most simple one, the most easy one, and the one that hopefully they still teach in school to these days. How do we allocate something on the stack? On any modern machine, usually you have a stack pointer that is a register. It points to where the stack is at any given moment. And so if you wanna allocate, you just take the current value, you assign that to some value, and then you increment by how big your allocation is. I'm pretty sure that this is the fastest way you can allocate anything because it's a register add. I don't think you can beat register add outside of maybe NOP. And even then, Intel engineers are really good. So, you know, you're basically in the ballpark of one cycle, potentially less. You don't need any library, you don't need any OS call. It's just the most basic thing ever. It has, of course, some limitations. For example, you need to know the size of the allocation at compile time. I know there's a caveat. See me later. But normally speaking, you know, in the normal C standard or C++ standard, if you try to stack allocate something, you need to know the size at compile time, so you can emit like a fixed size add on the compiler code. It's limited in space. Stack Overflow got very famous before AI was a thing, and that's a reference to the fact that you can overflow the stack very quickly, potentially, especially if you're on Mac or using threading libraries. Not saying that in particular for any reason, but it can happen. And also it's automatically reclaimed at scope exit, which is both a blessing and a curse. On one hand, you don't have to call free. On the other, if you happen to skip a pointer, bad things will happen. So I guess guideline number 1, prefer stack allocation when possible in regard to performance and everything else, because it's extremely fast. You don't need any special code. It's really easy to look at. It's really easy to debug. And unless you try to leak references to stack variable, you also get like 3D allocation. You don't even have to bother. Even in C, you don't have you have area even in C. Crazy stuff. Now let's talk about malloc. So it's better. I mean, it's better. It's better as in like it can do more stuff. So you can allocate an arbitrary amount of memory. And it's going to be alive until you call the matching free. I don't think I'm telling you anything very new right here. New. And of course, since we're doing C++, this is a C++ meetup, you should obviously not do malloc and free. You should do something like make unique or use containers. At least you should probably try to mimic the stack scope behavior by using a unique pointer or area of any sort to make sure that free will be called and you don't have to forget about it. You make sure you don't forget about it. Now, who knows here thinks that they know how malloc works? Okay, who thinks they can re-implement malloc? Okay, I still have some brave people. All right, to explain quickly what it does, right? Because the basic idea, and I'm not even going to go into implementation for a while, the idea is like, okay, you probably have a bunch of like blocks of a given size. That's usually most libraries what they do. They have a bunch of buckets with different like size allocation. You try to grab one, like you look for the size you're looking for and say, okay, do you have a free block in there? If you don't have any more, maybe like all your allocations of size 16 or 32 are gone, like you're out of those ones. Well, you just grab a free page somewhere that you obviously already have in your attached to your process. You just initialize it, add it to the list of pages of that block size, and then you're good to go. And of course, if your local like library malloc implementation is out of page, then you have to do an operating system call to call like whatever to reserve more heap space. I think it's BRK on Linux. There's probably some heap alloc on Windows. There's things like that. And if that fails too, because you also had a free pages on the OS, then your OS will have to find some processes that are basically using usually like a least recently used algorithm. They'll have to find some memory pages by your process or another process, page those out to disk or reclaim them if they can be reclaimed, and then they have to map them into your process, blah, 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 blah. So the problem here, or the learning, I guess, is the first one, honestly, you can implement that in a couple instructions. Like, it's not really a complicated thing. It is just like probably you can do a modular or like some kind of very simple arithmetic operation to figure out in which free list blocks you go. Then you just grab the pointer and then you return the thing. It's I don't know. I haven't measured it, but I think we're in the ballpark of maybe 10 instructions, something like that. It's really not that hard if it's already there. Of course, if you can't do that, then you have to start grabbing a free page from wherever you have to zero it, and then you have to initialize it, blah, blah, blah. This is not like perfect numbers, but roughly speaking, you go for like maybe another order of magnitude, right? It gets a bit slower. But then you're really unlucky, and there's no free pages at all, and your process actually needs to ask the operating system for more pages. Then you're probably in another 10x ballpark because you have to do a system call, and then you have to do a map, which has to do some stuff on your CPU to map pages on your processor, etc., etc., etc. And if you're really unlucky and there is no free pages, then you need to start doing disk I/O until you get some free pages, so you can actually map those for free, the page you freed up to your process. And I'm saying 10. If you're using an SSD, if for some reason you're still using like whatever other type of tape, or if a network drive, or I don't even know what it is, you're gonna have some fun time. So what I mean here is that guideline number 2, malloc is usually fast, except when it isn't. And the big problem is it's kind of impossible to tell. You cannot predict when that is gonna happen, and this is probably the reason why that guideline about not using malloc in like time-sensitive code comes from, is that if you're lucky, you can malloc a lot of stuff and you will not see it. And then on a bad day, you will malloc and then your entire application will freeze for like a couple milliseconds. And maybe a couple milliseconds is enough for your plane to crash or whatever other application you're doing. If you're on a video game, the most classic is you're gonna start skipping frames and you're gonna have angry people on the forums. So we're talking back. I think there was one brave man who said we can implement malloc, right? So usually the way it's done is that the free blocks and the pages are usually managed by your C library implementation, right? Be it libc or the Windows, I don't remember the name, but there's a DLL that does that for you. And everything that has to be with like virtual memory, paging and all that stuff, that depends on your OS. Which means if you are unhappy with the first two, you can say, you know what, I'm better than those nerds at Microsoft. I can do a better implementation of malloc. But if you still have the problem that you happen to be paging, you're out of luck. Unless you have your own operating system, there is no way you can just plug in that in. It's just if you have to make a memory, a system call to get more RAM, whatever your OS does, even if you think that you could do better, well, I guess make a patch on the Linux kernel, that's your best bet. But other than that, you're kind of out of luck. So now this is a quick aside to my friends at Microsoft, because the default allocator on MSC is not very good. I've explored. I had to discover that myself, like from first principles. First of all, maybe the most common one. If you do free of null on debug builds, it actually locks a mutex, a global mutex, if you're unlucky, which is really fun because this is defined in the standard as a no-op. Unless you're in debug on Microsoft, and then it just locks your entire thread. So that is why I've seen so many conventions says do if not null before calling free, and I was like, that's pointless. It's defined as a no-op in the standard. Yeah. Well, implementation disagree with the standard on that one, sadly, sometimes. And also, if you start allocating and freeing in parallel, you might realize that suddenly your algorithm is slower in parallel than in serial, because turns out it's really not good at allocating and deallocating the same size page, the same size of objects on multiple threads. Same thing. There's a bunch of locking involved. The funny thing is, there's solutions for that. Because there are some drop-in replacements for malloc and free on Windows, and a common one is called memalloc. It's the one that I've been using in some of the games I worked on. That has proven to be way more performant, especially in multi-thread. But wait a second. Who's making this? Microsoft? Yeah, I think they know that their allocators suck, but for some reason they can't roll memalloc as the default. I did not manage to get a message from Microsoft yet to know why. I have a suspicion that it's because they can't break backward compatibility with stuff that they written like 10 years or 15 years ago. But yeah, they know that it sucks. They literally have Microsoft Research make a better one, and it's open source and you can use it, and trust me, it works as a drop-in replacement very easily. And it does a bunch of stuff that modern allocators do, like it has per thread basically free lists, meaning that unless your allocation starts running out of pages, you can basically do log-free grabbing of more pages, more memory, etc., etc. It's pretty good at what it does. And really, when you have like parallel operation or threaded operation that all do allocations at the same time, you won't feel the pain the same way you would do with the normal implementation. So yeah, guys, number 3 is preferred third-party heap implementations on Windows. I haven't expressed so that as much on like Linux and Mac. I don't even sure. I think memalloc can work on other platforms, but I've really only I've seen the benefits on Windows. Cool. That was the theoretical part about like how is malloc, what is malloc, and how do I do malloc. Now let's talk a bit more about practices. So I used to work at a company that does video games, and especially they do map stuff with lots of tiles. So the test we used to do for new candidates was asking you to write a Pathfinder. And as one of the senior of the company, I spent my last 4 years reviewing Pathfinder tests every week. So I have seen a lot of code, and I've decided that is actually an interesting example of seeing like why do sometimes the performance of the thing that the candidate has turns out to be weird. Because what I do is that I had a ballpark, like, oh, this is roughly how much this test would take. And when I see something quite faster or quite slower, I try to take a note in my head at least of like, hey, what did they do different? Sometimes it's the algorithm, like they did something that is not as efficient as A* or whatever else, but more often than not, the problem is somewhere else. So I've noticed some interesting things over the years that I think are a good illustration of the common problems that people can do when allocating. Just as a refresher, if you ever have to do a Pathfinder or you want to apply to my previous employer, so the rough idea is that you have a grid, right? Like let's say it's a 2D grid to make it simple, like X, Y coordinates. The point is you check all the neighbors, right? You filter out the ones that are traversable and also happens to be within the bound of the map, just to make sure you don't fall off. And basically your recurs, right? That's basically what you do. It's a classic, like a breadth first search. You can do something fancier with A star, but roughly speaking, you start somewhere, you explore your neighbors, and you repeat the process until you found like the exit of the maze or the target destination, whatever else, and then you just record the path. So let's start by writing a function that will basically return me all the neighbors, all the valid neighbors of a given cell. That's all like a good building block for our algorithm. So we'll do a function. It returns a vector of points. Points being assumed to be a struct of like 2 ints. It takes a point internally. It's const because it doesn't change anything. Okay, cool. So what we do, we create a struct, and then we check. Okay, are we out of bounds? If we're not out of bound on X, then we do this. If we're not out of bound on X, but on the other side, we also add the rightmost neighbor. If we're not out of bound on the top, then we add the top neighbor. And if we're not out of bound at the bottom, we add the bottom. And then we return the result. Can you see some problems with this? How many people see a problem with this? Okay, only a couple. Okay, so here's the problem. Here you allocate, because you just created an empty vector and its size 0 and capacity 0. It has a usually power of 2 or power of 1.5 growth, depending on your implementation. It's not specified. But on my machine, it allocates a second time here, because it first reserved 1, then it reserved 2, then it reserved 4, and the last one is free. So I had 3 calls to mallocs and 2 calls to free. And then the thing is returned with an RVO, so that part is fine. We just get a move. But that's 3 mallocs and 2 frees. That's not great. Obviously, you can do this. This is maybe the simplest option possible. Just, an upper bound. You know that we cannot possibly find more than 4 points. So let's start with a reserve here. And then, we'll allocate once, because we have to reserve 4 points. But, it's one malloc versus 3 malloc and 2 frees. We're winning by a lot already. If I change that on your submission, I will already start getting way better numbers. So number 4, I guess, reserve final container size when known, rather than rely on geometric growth, because geometric growth is cool, but sometimes you can beat it, especially when you know the final size in advance. If you're doing a batch thing, for example, and you know how many items you're gonna go, if you can get any reasonable upper bound. If you don't, or if your memory is a concern, then maybe you have to be a bit smarter than that. But if you think you're in the right ballpark, a reserve will usually save you. Okay, that's easy until it isn't, because all right, let's see that now I got all my neighbors, so I'm gonna add them to a collection of existing neighbors, right? Because my algorithm keeps doing that in the loop, right? It finds all the valid neighbors and then it adds them to the potential candidate to explore. So I'm gonna write a function that takes like a collection of neighbors, and then what it's gonna do, I know that this time you have to reserve, because I'm gonna append 4 of them, up to 4 of them. So I'm gonna reserve in my global var, like a local run neighbors struct. I'm gonna reserve the actual existing size plus whatever I'm adding. So that way, when I'm copying all the points, I can be sure it will only allocate once, right? Because that's what it does, right? It allocates once at the top, and then it copies all my elements from like 1 to n, technically speaking. And well, I just told you to use reserve if you know the final size, and you happen to know the final size, right? The final size at the end of this operation is correct. This will be that. And that sounds okay, except you're going to be coding this in a loop. And the problem is you basically disable geometric growth by doing that if you do that in a loop, right? Because every time the vector has to grow, it will grow by exactly the right amount, which means every time it's going to have to reallocate. Because reserve is not using geometric growth. There is no way in the standard library to say reserve unless you would break geometric growth. That's an option on custom versions of vector. You can say reserve for at least that amount of elements, but please factor geometric growth in how big you should be. You cannot do that by the standard. If you say reserve that size, you will allocate exactly that size, unless you already have enough bytes, and then it will do nothing. but it will be really dumb and it will not save you. And basically what I'm showing you is how many allocs you do if you do reserve versus just relying on the default append. Yeah, one of them is logarithmic and the other one is linear, and you really don't want linear because that's really bad. So yeah, if you have a constant delta in a loop, do not use reserve for the new size plus x every time. That's killing the performance of malloc. Of vectors. Again, if you have a custom vector where you can actually say reserve up to, and it actually still does the best of geometric plus fixed size growth, then you golden. But if you use the standard, you're out of luck. There's no way to do that. Now let's zoom out a bit. Okay, we have made a loop that finds all the neighbors, and then we made another loop that adds those to an existing collection. And it's time to do an actual search queue, right? And if you've ever done something like that, usually what you do is that, okay, you create a search queue, you append the first element where you want to start on. Then what you do is you get the top of the queue, you pop it. Yeah, you can't do that in one. Why can't I do that in one call? I am still upset by this. Bryce, you worked on the standard. Why can't I do this in one call?
Bothers me too.
I hate it so much. So you pop one, then you find all its neighbors, and then blah blah blah. You'll probably do some filtering and add them to the queue, and then you will loop again, right? What's the problem with this one? No, the problem is find neighbors, because it does return me a new vector every time. It's better than before because that find neighbors does one allocation instead of the 3 we had, but it's still one allocation every time. And we already do an upper bound. We cannot find, but this function will never find more than 4 elements every time. So ideally, I should be reusing the same vector all the time because I can basically clear it and then reuse it every time. And that should be fine. And I would do one allocation at the start of the algorithm and I will be done with it. Well, the search queue might grow, but that's fine. That's geometric. There's not really a way we can do that. But at least that one, we don't have to every loop. We don't have to malloc and free for a vector of 4 because that's really wasteful. And again, that will show up in performance tests that I've done. So how do we fix that? Well, that's where I think you get the most controversial guidelines of all this talk. But first, I have to explain to you how I solved it, and then you will see why it's controversial. Because instead, we should take the vector by output argument as a reference, and then we just emplace in it. And then what it will do is that I'm not even gonna bother, like maybe the first 3 times you will allocate until it gets to size 4, and then it's never gonna do it, right? It's gonna clear the content and reuse it every time. I could reserve 4 if I wanted to, but I don't even have to. It's fine. It's gonna magically work. But yeah, so what I do is just every time I loop, I clear the previous neighbors, and then I reuse the buffer that I used the last time, and blah blah blah. I loop, and that way. I could do an optimized version of this that reserves 4 elements at the start, but honestly, at that scale, it doesn't even matter. What matters is I allocate only once, like the first time I run through like the first 3 neighbors, and then I'm done forever. It will never allocate anything more outside of just adding more stuff to the queue if I have to. That's good. That is way better. But that gets the controversy that some people will probably try to kill me for, but I will say, prefer output parameters when trying to return containers. Because if you use the return value, you cannot reuse previous allocations. And again, in some businesses, malloc is just too expensive to be done in a loop when it doesn't have to be. And again, I think it goes in tandem with the second guideline, which is reuse previous allocations when possible. And again, if I want to do 7, I kind of have to do 6. Technically speaking, you can pass in by move. And then return the same thing, like in a pure functional way of sorts. But I hate it. Bite the bullet and just take an output parameter. I don't have a better answer. If someone has a better answer, I'm interested, but... What?
A function object to visit this neighbor?
Yeah, you could have a visitor, I guess, and then do your thing. You can break it down, but...
Allocation? No allocation, no problem?
Yeah. I suppose that's the way. If you have a visitor, that should work, yeah. Some algorithm, it becomes a bit, it becomes a bit more tough, but anything that has to return a collection, it's better if you can pass the collection. Sometimes you can with a functor, sometimes it's breaking the abstraction a bit too much. Yeah, you could try to use small vector. That's the solution I got that got me hired. Every time I look back at it, I cry tears of blood because I had to do my manual implementation of small vector of 4, and I was like, why am I doing this? Just reuse a variable that is like 50 more lines, and also you don't have the bug that I had in my allocator that they didn't spot because it only happened in debug. Anyway. Let's talk about clearing stuff now. A thing we do often in video games is that we have this like frame of sorts. If you don't do frames because you don't do video games, you can think of a request scope, like if you're processing requests as a server of sorts. Any kind of basically main loop where you just do stuff for one processing and then you throw everything away when you're done. Well, I think I kind of gave the thing away, but let's continue real quick. So for example, in my frame, I have to, I make a renderer, it has to call for with some algorithm like a list of visible entities by the camera. Then we probably want to also do like what is actually audible by the current player, which is a mix of like, it's a combination of the state of the game and where's the camera pointing at. Maybe we'll have some debug message, blah, 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 blah. And every frame we have to clear it because every frame we're going to basically reconstruct all that data. And I've seen this a bunch. I don't know if you have seen this a bunch. Just assign to the default constructor. It has some advantages, I'm not gonna lie. The main thing is it's never gonna miss an element if someone decides to add something new and forgets to update the clear function, which I have seen a couple times. But it has an obvious drawback, right? Is that it frees everything I have allocated in the previous frame. And so every frame I will have to reallocate and have probably geometric growth reallocate, so X amounts of allocs for all the visible entities and all the audible entities where I don't have to because again, as my game runs, I kind of reach the maximum size of whatever my buffer of visible entity needs to be. And it's fine that I don't need to every frame reallocate this thing. I can just reuse it, but I can't do that if I use this pattern. So, well, the problem is it's reassigning containers actually, because reassigning containers, and I've checked every implementation of vector I could find, including like EASTL and other 3D version. They all do the same thing. If you assign a vector to another vector by move, they'll do a clear, a shrink to fit, a swap, and then they will return. That's basically what they will do. Just about all of them, one way or the other. I do not know why they do that, because every time the shrink to think happens, it just frees the memory from the previous one. And why does it implicitly free my memory? I don't want to. What I would like it to do is that if I'm assigning my vector to a non-empty vector, maybe you should not shrink to. Maybe you should keep me the memory. If I have a vector that's already reserved some space and you give me something empty, maybe keep the memory. Like, okay, delete the elements, sure. But keep the memory alive unless I actually want to shrink it because the variable is still alive. I probably might want to reuse that buffer. You can even be smart and try to check, okay, am I gaining some stuff by capacity because this one is bigger than the previous one, and maybe you try to save the biggest allocation, blah, blah, blah. There are many ways to do that, but no STL implementation that I have found do that, and I don't think it's actually specified that they have to. But it is an issue to me because then that means that this is the only way I have to do this thing properly. Which is that I have explicitly to call clear on every element, because that way I make sure that I remove the actual elements, but I keep the memory alive, so I don't have to do allocs every time. And of course, I run into the problem that if I had a new element and some guy doesn't know that there is a clear function or misses it, then I have funny times. It's usually easy to catch enough, but it's still annoying. And of course, these compounds, right? Because if my render function actually has an object itself and then blah, 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 and also it does an assign instead of calling clear, like every of my object, it's viral, right? Every of my object needs to have a clear function, and every one that contains those object has to call a clear function rather than rely on this pattern. Or else, even if I have a smart clear function, it won't be called in this thing. It will still just throw everything away and realloc. Oops. So yeah, sometimes I'm just saying, you know what? Just prefer member-wise clear over assignment to empty struct. It's more work, but when you're trying to save on reallocations, well, you clearly have a winner there. And again, this is coming from actual things that I fixed that turned out to be a big issue, because the allocation and the clear of a bunch of elements was way more expensive than anything else this loop was doing. Okay, now But maybe we can, instead of going that way, we can try to go another way, which is what if instead of malloc being expensive and us trying to avoid calling it, we made malloc cheap. So that way I don't have to care anymore, or I have to care less, or I only have to care sometime. So obviously, you know, as every good programmer, you look at your benchmark, the benchmark says malloc is slow, well, that's the solution, I have to rewrite malloc better because the provider tells me this is clearly where 80% of my CPU is. Fine, I can rewrite malloc, can't be that hard, can it? I mean, there's one guy in the room that says he can, so, you know, that's doable. Yeah, nobody, oh yeah, you're in the first row, you haven't seen nobody else raise his hand, sorry, you're being singled out. So, okay, malloc is a general purpose allocator, I guess, that's the main thing, right? It has to be good enough for everyone, every platform, every use case. So, obviously, you and your specific case is just like a very microscopic view of the entire ecosystem. Obviously, for your case, maybe there is a better way of doing malloc because you can throw away, like, I don't know, 50%, 80% of what it does because in your case, you don't need it. Yeah, right. You can't make assumption about usage patterns, and that's how you optimize stuff most of the time. The more assumptions you have, the smarter you can be. And obviously, you can have less compromise. So what do we do? So here's the first one. When people mention dynamic stack allocation, there is a horrible thing that is not standard called alloca. It's not standard, but also it's available on every compiler that is like used by real people, as far as I know. At least it's the three main ones have it. Maybe there are some other funny ones who don't. But it's very common. What it does is it's dynamic stack allocation. It's basically going back to what I did before, you know, like the add to your stack pointer, except it's done at runtime. So it takes an arbitrary value. It's a C API, so you lose all the ARII. So if you have to construct an element in it, you have to manually new in place, and then you have to remember to call the destructor. You can make a macro, like is what I used to do in the past, my older days, that does both of those things, so you actually are sure that the destructor will be run and you avoid some issues. And again, it's fairly fast because it's basically gonna be translated to one register add by your compiler at the end. It's usually not even a function, it's a compiler intrinsic. So it is really fast. What's the problem? Well, you're still bound by stack size, and again, I have had players unable to start my game because turns out the stack size is really small on some operating systems in the non-main thread. So yeah, you have limited space, again, especially on threads, especially on macOS. Yes, this was a crash. And again, it is impossible to set the stack size when you spawn a thread in standard C++. So you can't even fix it that way. You can try to do stuff with custom libraries, but I just would not rely on that. I would just say avoid using alloca unless you like overflowing the stack. That would be my guideline number 9, because I have seen it more abused than used. Most of the time, the previous guidelines will give you a way to do a cheap alloc that is better than this. The most common would be just have a buffer that you reuse that is just used for that space. Yes, alloca will allow you to conflate all those usage into one and make sure that it's only one that is always reused. But again, we have solutions. We can move on a bit to custom allocators, for example. You can have special allocators that do something that is simpler than what malloc does, and so it's very fast, hopefully. And in various libraries and in the standard since C++ 17, you can actually have a lot of custom allocators. You could have them before polymorphic allocators, but as far as I'm told, people didn't like them. PMR makes things better. And then you can decide to say, okay, I'm gonna throw some of the constraints that malloc has, or some of the benefits of mallocs because I don't need them, and instead I get something better. I'm not gonna redo this talk because basically this is the talk you want to watch. It's called Taming Dynamic Memory Allocation: An Introduction to Custom Memory Allocation. Oh, that's a long title. It's by my good friend Andreas Weiss. It's at ACCU 2019. There is also a version at Code Dive, and there's probably a third one. I think this is the longest one because ACCU is usually 1 hour and a half, so you have a bit more time to develop your topic. And it tells about his experiences, especially in embedded, of trying different custom allocators and seeing what you can do with them. I'll just try to give you like the Cliff Notes version of it. So the simplest one are monotonic allocator, right? You allocate, you take a vector, you make a vector or an array of size x, and then you basically emulate what the stack does. You start at 0 or like an offset 0 in in that buffer, and every time somebody tells you to allocate, you just allocate, except you're not really a stack because you don't want to keep things out of order or anything else. So if someone calls free, you just do nothing. And it basically keeps growing. It grows, it grows, it grows, it grows, it grows. You cannot deallocate a specific object. The free on a monolithic allocator does nothing. It's actually a feature in some things, because if you don't need to run the destructor, then you can say, okay, at the end of the frame, everything that has been allocated for this like per frame allocator, just reset the pointer to 0. Don't bother. I've done that in a few places. I recommend having a static assert that no object you construct with this has a custom destructor, because else you will have funny issues. But it is possible, and it allows you to just have like one running buffer that you can reuse as much as you want and then reset to 0 when you're done. You can also do that if you just need to grab a buffer at some place. You can use that to drop as a drop-in replacement for Alloca. Usually what I do is I have like 1 or 2 available per thread, and then I just say, Fred, just grab the one for this thread and then use it until you're done, and then just reset it to 0. That works pretty well. It's simple enough that you can basically make a slideware implementation that is mostly correct, which is just like you have a buffer. It has it's a vector of bytes. Well, it's an array of bytes really. It has a pointer to the current place, and then the allocation. We have some like funny math at the top just to make sure that you work with alignment, because alignment is the thing we have to do. I don't try to be smart here. I just align everything to max align t, because that's what malloc does, and we just don't want to be too smart about it. And also that make sure that everything will fit neatly. You don't have to do padding or anything else. So it's a very basic way of doing that. That's basically it. That probably translates to like 3 instructions or something, because CPUs are really good at doing OR masks and other things like that. That looks very scary on the slide. It's just basically gonna take your size, take your current pointer, do some math, and then do one or 2 adds and be done with it. It's good. And then the deallocate is extremely easy to implement because it does nothing, and the deallocate all just says, okay, reset the buffer to the start, and then you're done. Again, like, it's an allocator that fits in 2 slides, and it does exactly what you want. It grows until it runs out of memory, and then you crash, or maybe you have an assert. I don't know how you want to do it. Again, if you can have a budget, because the main issue of this is what do I do when I run out of space? Because on most modern operating system, like, technically malloc can fail, but most of the time it won't. It will just page more stuff out. It will continue growing, or you have to go to a crazy point that you really run out of operating system size. This one asks you up front, what's your budget? Because I will allocate it up front, and then I can't go over it. If I go over it, you're in deep trouble. So the classic people love to do is game levels. You say, okay, for this given level, you will have a bunch of allocators for like assets. For example, like you have one allocator for all the models, one allocator for all the entities you will create while the game is played, and another one for all the textures, something like that. And then once you're done with this level, we'll just yeet all the stuff out, and then we reset it. That's very convenient, and it has the added bonuses that it forces your artists and designers to make sure that they can't go over because the game will crash. Because my games usually didn't do that, and then you get people from the lab calling you and say, that release you're about to make, it's slower than Crysis. And my game don't look like Crysis if you ever looked at what I used to work on. They kind of look like, I don't know, something 20 years before Crysis. So yeah, no, yeah, that's embarrassing. And so that forces people to have a budget, which can be a good thing. It at least forces a discussion within your team of, hey, how much memory should we be banking on this thing? You also might discover some interesting assumptions that you have made that were entirely wrong, such as how much memory does this thing use? State machines, also a good thing, request processors, any transaction, basically. When you start something, you do all the stuff, and then you want to make sure you yeet everything out at the end. It also bonus, nothing will leak afterwards, because you will just throw everything out. Drawback, nothing will leak afterwards, so if someone keeps a pointer, by being very naughty, you will have a very interesting free memory read to follow. So guideline number 10, consider monotonic allocators when resources can be both scoped and budgeted. You need both of them, right? But that's a bit like restrictive. So what if we could do better, right? What if we added a free list? That's usually the first step after this, right? Say, okay, I have a free list, because you can add a free list on top of a monotonic allocator. It's actually kind of simple. I'm not going to explain all of it, but basically the idea is that every time you return like a past allocation to the thing, you just save the pointer to it, and then you make a chain link list of the free buckets. And then if that's failed because there is no more thing in the free list, you just append to the end. It's easy enough to implement. It can be made atomic. It's not trivial. It is doable because like atomic add and remove from a list only at the end is a solved problem. Just don't try to re-implement it yourself because I thought I could, and turns out there's a thing called the ABA problem that is really not fun to do, and your naive implementation with compare and exchange will not work. So I don't recommend doing that by yourself, but you can look up on the internet. Some people have done it. It has the obvious drawback that repeat allocs might not be contiguous, because since you have a free list, maybe you end up reusing memories from a previous alloc rather than appending at the end of the array. So if you're the type of person who really wants to rely on the fact that if you suddenly allocate 10 assets for a given level and you expect that they will all be next to each other and it will be really nice when you process them later, well, you might lose that in the process. But then, of course, there's a problem with that, is that you start wasting a lot of memories if the allocations are not of the same size, because the buckets that you free might not be of the same size. Of course, we can also solve that because, we can start having a routing indirection that just basically chunks your allocation into different buckets. Of course, when you do that, you need to find a way to do the reverse operation from delete, because delete doesn't give you the size. Again, that can be solved. You can look up the address range and say it falls into this bucket, blah, blah. What are you doing? Hold it right there, because I have a bonus guideline to you, and it is that for each feature you add to your allocator, you're one step closer to re-implementing malloc, and you need to know where to stop. And what I've gotten from my conversation with Andreas is stop at monotonic. Anytime you want to go further than monotonic, stop. Just use malloc or just find something else. Some people in the game industry have made the argument, someone I argue sometime on Twitter with, that argues that no free list is where you should stop. I'm not 100%. I think it works, but then they start basically having specialized allocators for one given object with a free list. Because then the size is not a problem, so you only have to handle the fact that you have a free list, and you need to make sure you have an atomic way of going back, unless you don't need multi-threading, and then it's easier. But still, you're playing with the line, I would say, and yeah, there's a good chance you're gonna skirt over. All right, so I don't know how fast I've gone at all. Is there a timing on this thing? No. Okay, cool. I have no idea, but I'm wrapping up, and then you can ask questions if I have some time, or shut me up if I talked too much. So, in conclusion, just to recap a bit, dynamic allocation comes at an unpredictable runtime cost. There is no way you can predict it in advance. So you can try to be smart about it by pre-reserving a bunch of stuff, but eventually you run into the problem that you're out of RAM and you need to swap stuff out, and that's not fun when that happens. Size up allocations as much as possible once, if you can, and reuse containers as much as you can, because again, we're trying to save on how many calls to malloc and free we're trying to do. Consider monotonic allocators, but beware of going further, because this is a very dangerous rabbit hole / slippery slope of basically ending up with your company having a custom malloc that is worse than malloc on most cases. I have one question before I finish. How many people thought that they had we're gonna do by dichotomy, that's gonna be faster maybe? Oh no, you're gonna raise your hand. Did you have at least one guideline that was useful? At least one? Yeah. 2, 3, 4, 5, 6. Okay, you're very good experts, because that's basically at least 4 of them were not very useful. Okay, that's not too bad. Okay, right, and furthermore, I still think your build should be destroyed. Thank you. If you don't understand that quote, I will explain later. And now I can take your questions, if you have any.
So how did you finally implement pathfinding
algorithm? That I will. I will leave you if you want to apply there. I think some people have put their own implementation on GitHub, but I mean, it's an A star, right? It's kind of a solved problem. The main thing I have to say is just don't allocate in the loop if you don't have to. Yes.
The question may be a bit weird, but what you showed us is that we can manage allocation at multiple levels.
Yes.
In this case, there is at the container level,
yeah,
or at the allocator level.
Yes.
and I often struggle to choose between one of them. Do you have some kind of preference between one of them? Do you use them both?
So I think allocators are really good when you want to do scope stuff. So basically you have to say, okay, I'm creating anything that I'm allocating under this call stack will go into this cheap allocator, and then once I exit, everything will be reclaimed. The difficulty of implementing that is you really have to make sure that there is no side effect in destructing your objects, because usually that's better. You can not do that. You can let the destructor run normally using like RAII, and then make sure that you just care about freeing the memory, but it's usually an added bonus that people like. But yeah, if you can scope, like say, okay, I have a thing, anything that's supposed to, like, you can maybe even enforce it in the API, say, okay, like, you attach your request object, for example, you have like an allocator, and people can do like request.allocate or whatever, and you're guaranteed that all the memory that is allocated through this like request object will die at the end. The main thing you have to do is to make sure that nobody will ever try to keep a pointer to that stuff after, because people sometimes like to keep pointers to stuff. I know some modern like memory safe languages are a bit better at doing that. I think you might be able to use like a custom tag pointer to make sure that people can't assign those in the wrong places and whatnot. But yeah, if you can scope it, basically. And then, yeah, the one problem is that unless you're willing to, for a given scope, replace the global allocator like temporarily and then put it back, you will have to pass an object to every caller to say, hey, by the way, if you ever need to call malloc, actually call this. You could potentially, for a thread, just say, okay, under this scope, just replace malloc with this, and then once we're done, just put back malloc where it was. But it's a bit risky.
Yeah, I think the way D handles this problem is by having two global allocators, one for each thread, one global allocator for each thread, and one global allocator which is shared among threads, and that you can modify when you need a different allocation policy.
I see. The way the malloc works with the lib from Microsoft, for example, the good one, memalloc, is that you can free from any thread, but they have some smart way of basically transferring ownership of memory when you free on a different thread, and keeping the free list together. I don't know how they do it, but it's smart enough to not lock all the time, so I like it. Yes?
A few questions from Loic.
Yes.
He says, reserve is allowed to allocate more than requested and may preserve exponential growth.
Okay, I've never seen that done, but
Why for the stack? Why top and pop? It's to be exception safe.
Exceptions. Yeah, I guess that makes sense, because else you wouldn't know what to do. Well, I don't play with exception that much.
And finally, his question: why didn't you mention in-place vector?
Because it's, I guess it is about memory allocation to some degree, and we discussed this. I think it's a very specific. It's more of a container thing, right? It's yeah. You can have basically you could have a container that has a static size and does like dynamic allocation, because Start Array doesn't, for example, right? So you would have to keep a size going somewhere else. There's finally one in the standard, I think in 26 or is it 23? 26, right? Yeah. In-place vector, I think it's 26. So yeah, I guess maybe one of the reasons I didn't mention it is that most people do not have access to this unless they use third-party libraries. I think Boost probably have a bunch.
26.
Yeah, and then you have the question of like, do you want one that can grow after a certain size, or should it just explode in your face if it can't? Yes, and again, that's what I did when my Pathfinder submission back in 2017. It was a lot of code for just trying to solve a Pathfinder, and turns out, I don't know, sometimes I just like stuff that is easy for people to read, and just doing reserve and then reusing the buffer is just simpler.
For move assignment, I think it is that the iterator, if we have an iterator from the value, it should be still valid. So we
All right, because move assignment from the right one does not invalidate in the iterators. Yeah, I guess I care more about the other one, but yes. Especially if you move from empty, right? If you assign from empty. Cool. Any other question? Thank you then.
Thank you very much. thank you for today, for both our speakers, for you, for the attendees. See you next month, I hope. You will be informed as soon as I found the host. Thank you. Thank you.